This is the New Quantum Era. I'm your host, Sebastian Hassinger. A little less than a year ago, we were shooting a documentary of the physics conference on the island of Helgoland for the centenary of quantum mechanics. Helgoland is the rocky North Sea outcrop where Werner Heisenberg, by the standard origin story, worked out matrix mechanics in June of 1925. The roster of speakers was studded with Nobel laureates, and on the first night, at the opening banquet, one of the speakers stood up and thanked the organizers for having the courage to invite a philosopher of physics. That speaker was Elise Crull. She's associate professor of philosophy at the City College of New York and the CUNY Graduate Center. She was named a fellow of the American Physical Society in 2025, nominated by the APS Forum on the History and Philosophy of Physics for, among other things, recovering Grete Hermann's contributions to the Foundation's debate. And in late 2024, she and Guido Bacciagaluppi published The Einstein Paradox with Cambridge University Press. It's the most complete archival reconstruction we now have of the debate that the 1935 EPR paper unleashed, and much of the correspondence in it has been published or translated for the first time. I wanted to talk with Elise because I think we're at a very strange moment. For 100 years, the interpretive arguments about quantum mechanics, what superposition really is, or whether the wave function is something out there in the world or something just in our heads, could be treated as more or less an in-house philosophical conversation. The formalism worked, and the various interpretations could just fight it out at the conferences. That truce is over. Quantum computing has dragged those questions into the fab and into the budget meeting. When a hardware team distinguishes decoherence from noise, when a paper claims a speed-up from circuits with indefinite causal order, when a marketing deck says the machine exploits entanglement, those are interpretive choices, whether anyone calls them that or not. So we talked about what philosophy of science is actually for at this particular moment in quantum physics. We talked about what Einstein was really worried about in EPR, which it turns out isn't quite what most people think. We talked about indefinite causal ordering and whether the experimental results are telling us something deep about causation or something deep about the limits of our classical vocabulary. And we talked about the history Elise has spent years recovering from the archives. Grete Hermann, Herta Sponer, and what that history predicts about the origin story quantum is right now writing about itself. This episode is brought to you by Outshift, Cisco's incubation engine. The need for computational power is rapidly increasing in every sector. From drug discovery to material innovation to complex financial modeling, classical systems are reaching their absolute limits. It's time for a paradigm shift. The answer is a scalable quantum network built on open standards and vendor-agnostic architecture. By uniting distributed quantum devices, you unlock limitless computational power. Learn more about the Cisco Universal Quantum Switch at Outshift.com. Here now is my wide-ranging conversation with Elise Crull. Hi, Elise. Thanks for joining.
Hi, Sebastian.
Good to see you.
Good to see you.
We met on the island of Helgoland a year ago, coming up on a year ago, for the 100th anniversary of physics. You were among the speakers of the first evening at the banquet that kicked the whole thing off. And you opened by thanking the organizers for the having the courage to invite a philosophy of physics person to so explain a little bit about how you not got to Helgoland, but got to your profession of philosopher of physics.
Oh, that's a fun one. So I was a physics major, physics and astronomy as an undergrad, and I really loved it, especially once we got done with like the Newtonian mechanics and classical mechanics. Ugh. But when we got to quantum and relativity, I was like, this is just wonderful. And I was always asking sort of historical questions of my professors, and I went to a small liberal arts school called Calvin University. And so the faculty were really tolerant of me and sort of encouraged me and gave me readings and books, but they themselves, didn't have historical or philosophical training. And so oftentimes we sort of just ended there. I would ask, but how did they know that this was the right equation for entropy or something, and they just didn't have an answer because they weren't taught it. And so I was doing research one summer on astrophysics using Fortran 77 and realizing that as much as I loved physics and I knew I wanted to be I knew I wanted to be a professor, I wanted to do something different. I wanted to engage with these other questions. And just serendipitously, that same summer, I sat on an interdisciplinary sort of working group called Aesthetics and the Disciplines, right? So one of these cool things about a small liberal arts college, and I was supposed to be the student researcher on physics and beauty. And I got into it, and I thought it was really fascinating, but the philosophers or the physicists were saying, interesting, but only a little surface level stuff. And during this colloquium, I met a woman who was a graduate student at Notre Dame, and she said, "Didn't you know there's a whole field called philosophy of science? And in fact, at Notre Dame, there's history and philosophy of science graduate program." And I said, "That's it. That's precisely what I have to do because I want to teach and research the kinds of classes that I wish I could have taken as a physics major." So that's what I'm doing now. It's a pretty great gig.
That's awesome. It's awesome, and it really it's interesting how right from the start that it feels like as you do now, you have this sort of counterpoise of like looking back and trying to understand where physics has come from, where science has come from historically, but also looking forward and trying to understand how that informs or might predict or might point towards solutions to challenges that we're facing now. So do you sort of see it as in that in between space?
Yeah. To be honest, I wasn't as excited about the H part, the history part, and history and philosophy of science until I began to study it. And then I just realized humanity is asking the same questions of the world and of science, but in new and very changing contexts and with different voices. And so when we study this history, we see the same question in its different iterations in different historical contexts being asked by different people and so on. Uh, and it just really changes. It just makes a tapestry sort of form around present day questions and future looking questions that I think you can't come up with any other way. And so the more I learned about it, the more I realized, yeah, this has got to be a part of how we do science. It's so crucial, especially in quantum theory. Yeah.
Yeah, and that's I mean, that's what was so interesting about your presence, your participation in the Helgoland conference, which was 100th anniversary of, Heisenberg on the island, doing what he did. And but also was very interested in this moment of quantum information technology, right? We're starting to use the formalisms that have worked are now emerging from the university lab and going to the industrial R&D lab and are turning into practical tools, or hopefully it will be practical tools. And I mean, at that particular moment, what's the role of philosophy of science in that kind of transformation and testing of those formalisms?
Wow, that's a great question, Sebastian. So I think there is always a role for history and philosophy of physics. And I know it's in my vested interest to say such things. But I genuinely believe it's true. Because every aspect of science we do requires interpretation because the world isn't just out there. We make choices about how to encounter it. What are the relevant parameters? For what amount of time do we need to collect data? How do we interpolate between the data? Right. So there are moments of interpretation everywhere. But being one of the things that Einstein said when he was, uh, uh, beginning the revolution of relativity in the early tens and of the last century, was that some of the old Newtonian worldview, the concepts of like absolute space, absolute time, what inertia meant, that these concepts themselves needed to be revised. And there's a way that philosophers, maybe on a bad day, we're just sitting around saying, but what do you mean by the word velocity or whatever? But this is precisely the sort of reevaluation of the terms in physics that Einstein said led him to his insights. And I said a little bit in my speech at Helgoland, but there's a way that terms like causation, like entanglement and decoherence, which were forbidden or unknown words for decades in physics, really set us back. But now decoherence and entanglement are precisely at the heart
Right.
of this information science growth. And so knowing what these things mean, I mean, even the fact that there are maybe 6 or 7 definitions of entanglement that are being used in physics that I could give you, and then a few more from philosophy, mean that it's a time where the paradigm is exploding with all these different ideas and thoughts and creativity. But that's exactly where we get philosophical, and we can say, okay, but what is this word doing? Like, what do we mean by entanglement in that context? And does that say something about causality that it doesn't in this other experiment? Or even, I was speaking with some physicists at Duke the other day. How you tell the difference between decoherence and just noise? Are these different things? And because one we can shield for and do quantum error correction, and the other is something else. And so there are all these emerging different use of terminology. And that's one way I think that philosophers, or at least the philosophical impetus that I think most physicists have, because they want to know the why of it.
Right.
And that's kind of exciting to see how it's driving. And of course, they're the engineers and the more pragmatic folk, but we have to approach these problems together.
Yeah.
They're not.
It's funny. I was just rereading Charlie Wood's piece in Quanta about the Helgoland conference, and you just remind me of he said within minutes of sitting down on the ferry, he heard one physicist say to another, "What do you mean? What do I mean by what do I mean?"
It's natural, right?
It is.
So it's not the thing philosophers do. It's just when you step back from whatever it is and start to think carefully about it, those are the questions that arise. It's just that philosophers have we've been trained with a particular tool set to sort of deal with these puzzles. And well, I'm mixing metaphors, but you understand. Super exciting time to be a philosopher of physics, I gotta say.
Yeah, no, I mean it's really interesting because the joke about philosophy is always the sort of the pointlessness ultimately of those questions, but we're actually exactly the point where they're crucial. As you said, the difference between decoherence and just being overwhelmed by noise that's an incredibly subtle, frankly, engineering question. As you said, you can do something about noise. You can't. You just have to understand how decoherence behaves and what physics is going to create decoherence rather than guard against. Right? I mean, those are very, very different challenges.
Right, and thinking in particular about what is information supposed to be. And so when we talk about various kinds of entropy, I mean, I was on a panel with a bunch of entrepreneurs the other day, which was very enlightening. And I realized I'm in the right career and I have no place in business. But one of them was talking about a model they call entropy something or other. And I said, but what kind of entropy? Is it Shannon entropy? Is it like thermodynamic entropy? Is it von Neumann entropy? And this is the chief scientific officer who's like, I don't know. It's kind of relevant, right? Because these are different phenomena.
Yeah.
So, right. Yeah. So it's, yes.
Yeah. Well, and I mean, it also brings to mind, the Copenhagen interpretation of quantum mechanics. Merman famously characterized as being shut up and calculate, right? Which sort of, that is a version of what you just described. It's like, the math works, so don't think about it. But it seemed on Helgoland too, there was a vigorous debate about interpretation, and it seemed
Yeah.
in some ways that that it was a lot of it has to do with trying to reconcile relativism with quantum mechanics. And you wrote just a year and a half ago, you brought up Einstein paradox.
Yeah.
What was sort of the motivation, or what's the sort of the 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 most relevant sort of aspect of the revisiting the Einstein Podolsky Roden paradox?
Well, I think it's interesting that you bring up the EPR, right? Einstein Podolsky Rosen paper from 1935 in right after a question about the measurement problem. Because of course that it wasn't called the measurement problem then. And that wasn't explicitly their concern either. It was a combination of really interesting philosophical questions that were deeply a part of the physics, figuring out the formalism itself. And so part of what my co-author Guido Bacciagaluppi and I knew going in was that these early physicists understood that there's no meaningful distinction between doing physics and doing the philosophy of physics. What it meant. So Einstein was motivated by the question. They were talking about whether or not quantum mechanics was incomplete. And by this, they meant something about determinism or something about could it be that we haven't yet discovered certain hidden variables that could make it complete. And they don't know this yet. And so they're arguing on philosophical grounds, not just about whether the formalism is complete, because the formalism was logically complete, but this other sense of what it means to have a physical theory that properly captures what's going on in reality. And that is at the heart of their conversation. And so it's not about the measurement problem per se. It's about incompleteness and what it means to have a full physical theory and how does it map onto the world. And for Einstein also, we have this theory of microphysics theory, but it doesn't seem to track. The formalism doesn't seem to track at the macro level, but we're pretty sure it should.
Well, and as you said, it doesn't,
Yeah.
right, and it doesn't feel right. I mean, his objection to spooky action at a distance is that he doesn't think that he is playing dice with the universe, by which he means, as you said, determinism. There's this sense that there's an unease with the idea that that the universe, that reality isn't mathematically solvable, that it isn't ultimately the result of a giant equation that's like deterministically solvable, right? I mean, there's that tension right at the core of it. It seems.
So that is definitely something that many people in this early conversation are expressing. But one of the things my co-author and I found that's very interesting, and we kind of knew this before, it's like Einstein scholars will hit you over the hammer with a hammer nicely. He wasn't as concerned about determinism as you would think. Because one of the things he realized from general relativity is that in 1913 to 1916 is that he has the Einstein field equations don't pick out a unique universe, a unique space-time. They give you a class of diffeomorphically invariant solutions, any of which could be, the way it is. So, and probability is at the heart of some of his favorite physics, like thermodynamics and stuff, right? So it's not that we use probabilities that bothered him. It's not, even a question of determinism. For him, it was precisely about what does it mean to have a theory that connects to the world in the right sort of way. And for him, that meant that the mathematics had to have a one-to-one mapping. And determinism might be a part of that, but he also believed that the world was such that individual systems had their own states. And those states sort of clung to those systems. And even if they interacted, we could sort of separate those states apart and re-describe the initial system by itself. And so that there was this weird property such that interacting quantum systems, even after they cease to interact, still cannot be described with their own wave function, but they have to be described in this inseparable or non-separable way, which Schrödinger, after their conversation, calls entanglement. This was an entirely new feature of the world, right? And so yes, it's somewhat to do with entanglement or with determinism, but it's also to do with, what does it mean for two systems that are now like separated by relativistic, like they're space-like separated, can still share information somehow.
Yeah. Yeah.
And on the stage at Helgoland, like the guys who won the Nobel Prize for proving non-locality
Yeah.
couldn't agree on what this meant about the world.
I know.
So
That was my favorite moment. It was sort of like,
that was the moment I thought, okay, I'm gonna have a job for the next for the foreseeable
definitely
future.
job security.
Yeah, exactly.
We're not going to arrive at a moment where it's like, okay, solved.
Yeah, exactly. And also the conversation there, it was like a lot of the preeminent physicists there, and there were many, thought that whatever the next theory would be, whether or not it was quantum field theory or some successor theory of that, it was going to be stranger.
Mm-hmm.
You remember that? That
Yes.
it was going to be even more wild and more conceptually stretching. And that also made me really excited.
Yeah. Well, and that's a good segue to some of the work you've done that I think is the most exciting in terms of bridging from philosophical weirdness to practical implications is indefinite causal ordering.
Yeah.
And this is quantum circuits on real quantum computers that show a speed up over a classical algorithm because there's the A causes B and B causes A causal chains are in superposition.
Yeah.
Which, I mean, wait a minute. Okay, explain that. Or try to.
Can't. Yeah. So I think what it indicates is two things. And I haven't like published this yet, but I've given it in talks a couple times. I think the first thing is like when I read these papers and talk to the PIs in these labs, I don't think this is where clarity around concepts works. So they're aligning the word causality, which in philosophy is a rich and complex term. They're equating it to signaling constraints. But those are very different things because I might send you a signal and it has no causal.
Right. Okay.
You do nothing with it, right? Okay, so there's some separation between what this word means, and so when they're saying that A causes B is in a superposition with B causes A, it's not clear that they mean something like counterfactually robust. Like, had it been that A had not sent the signal, then B would not have responded. Right? Okay. And so it's unclear what these results mean. And then there's also the physics question of, are these genuine results in the sense that we haven't built into the systems some kind of causal dependence already? And I don't think those questions are settled yet, but they're fun ones. Like they're really a unifying of philosophical and physical questions. But I think they have shown something undeniable. Like the phenomena do show something. I suspect it has more to do with temporal ordering than anything causal, and that's still plenty weird. Like that A coming before B can be superposed with B coming before A, but whether or not it's causal or temporal, this is the second thing. I think it just indicates that we still interpret the terms of temporal ordering and causality in irreducibly classical ways, and that's just not, those descriptions do not grip quantum states of affairs. And so it might not mean that we're violating these things. It might just mean that these things were defined and understood classically, and that picture doesn't apply anymore.
Right. And you've argued that taking classical causal relations for granted sort of limits our view of nature, right? And
Yeah.
so is there what do you think? I mean, there are many conceptual misstatements sort of currently in the quantum industry. I'm going to bring it back to quantum technology now. Like, are there, misinterpretations of superposition, of entanglement, of others sort of that you think are the most misleading at this point?
I don't think I'm the right person to weigh in on. I mean, I think we all could do with some caution, but I also understand that scientists who are publishing these papers are under extreme pressure to get pubs out with sexy titles, and that's not to impugn the physics at all. Like, there's really interesting stuff going on here. But that's why I want to, be in conversation. But I think there are some. The only thing I know is, I don't want to cast aspersions, like from my metaphysical armchair. But I think being precise about how people are defining entanglement, like whether they're using it operationally to mean like the density matrix has off diagonal terms, or whether they mean something like we violate Bell's inequalities. And so there are some physics works along these lines, and that's great. Where people are saying, like in quantum communications, okay, this setup, it doesn't violate Bell inequalities, but it still has what look like non-separable states. It looks like we have intent. So nuance about that is really important. And I know some folks are talking about classical entanglement. But so that's the one thing where I cannot deal with that. I think what they mean is something like no, it's not classical correlations, but the very definition of entanglement is that it cannot be described classically. Well, that seems really confusing to me, but I think what the physicists are doing is trying to explain that there can be all these diverse, not just definitions of entanglement, but that entanglement itself is a really complicated relationship, right? It's not a relationship between systems, it's a relationship between properties of degrees of freedom. Yeah, that it's relativistically constrained as well, right? So, like, what space-time foliation you're in, like, will determine whether or not you see particular things as entangled. And maximal entanglement that leads to monogamy of entanglement is only with respect to one degree of freedom, right? So I could have two systems that are monogamous, like maximally entangled in spin, a singlet state, and people say, oh, they're monogamous, so like they cannot be coupled in any other way. It was like, no, they could still be coupled in translational degrees of freedom with other things. So just understanding the richness of this concept is how is already being exploited in good ways, if exploited can ever be used in a good way.
Yes. I think an idea can be exploited. That's totally fine.
Yeah, entanglement harvesting and things like this.
Yeah.
Like really cool stuff.
Yeah. I mean, you use the term conversation, and you've referred to sort of different voices, and you've made the point that in the past in your work that theorists and experimentalists need to be in deep conversation to really be effectively driving the field forward. And in particular, what I thought was really interesting is your sort of reexamination of the relationship between theory and experimentalists in physics is actually in part a camouflage for the implicit sexism in the field, right? That women were often sort of quote unquote relegated to the lab where they did the unimportant work, but in fact they are, they're full experimentalist physicists who are in having those implicit conversations with the theorists who happen to be mostly men, and driving the whole field forward. Is that something that, like a view that emerged out of the sort of the broad historical investigation you were doing into the history of physics, or was that something that you wanted to sort of address directly, the role of women in physics,
so two things. I think exploring the role of women in physics is massively important. But second thing, it isn't primarily what I'm interested in. But it came out of this work in the primary, like the archival source materials. It was undeniable how important this was. And it's interesting just from a sociological perspective. My teachers and the generations who were doing history and philosophy of quantum in particular in the 70s, 80s, 90s, they were getting their hands on this archival material and like Kuhn's archive for the history of quantum physics and all this stuff for the first time, and doing interviews with some of these people like Bohr, Schrödinger, and others. And so all of that scholarship in those decades was really focused on these canonical figures. But that's been done to death. And so now people are going back and saying, but this history we've been given, like maybe it was the best history available at the time, to be charitable to the historians then. But also the way that we do history has changed immensely. My generation doesn't do internalist history of ideas. Like that is not considered appropriate anymore, which is the idea that it's a single person in a room who, like, without any needs, social or physical or economical or political, is doing their science in a vacuum, right? Not true for anyone. And why this is so important, especially as like a professor at City College and other places, like when students realize not just that science is a social endeavor, which they get, but that the scientists themselves, even Einstein, needed his buddy Grossman to help him out with the math for general relativity. Like nobody's working alone. And the interactions and the debates and the tensions and the friendships are what made science go forward. It gives them permission to become scientists of a different kind, like in their own body, with their own minds. And so I think just working with the scientists of the future, just seeing how important it is to them to realize that the actual story of history is a really cool, complex, more diverse than you thought it was state of affairs. So yes, not primarily a historian of women in quantum physics, but anybody who does justice to the history sees there's no way the big dog theorists could have done anything unless data about various element spectra and the energies of dissociation of diatomic molecules and how crystal lattices were like, this is at the core of the early papers in quantum mechanics. And so it's a huge part of the story, not just the data, but how we got them, right? And then how the experimentalists themselves started saying, like Herta Sponer started saying, hey, this quantum theory, like we need to use this. Like this is the right theory to use in our experiments going forward.
Right.
So, yeah.
Right. Was it Sponer that you described as like Bohr, but better?
No, well, so that's
or
a phrase
Grete Hermann.
Guido Bacciagaluppi, my co-author Guido, coined that phrase, but we're both on board. That's Grete Hermann, who was not an experimentalist. In fact, she was a mathematician, PhD in mathematics under Emmy Noether, and then she got interested via her conversations with Hilbert and Heisenberg and other people in quantum theory and understood it, and then became a rising star in this small neo-Kantian school. Truly an interdisciplinarian. So she didn't do any experiments, but from a theoretical and philosophical perspective, she was so brilliant. She was so brilliant. And like she wrote these few papers and then dropped the mic. My very perhaps too nice way of saying like she went into exile during World War II because she was socially active against the Nazis. But then she dedicated her life to ethics and education and things that women actually typically do in these eras and still. And she wrote the Weizsäcker in the 80s and said, I'd really love to do some more of that quantum philosophy stuff because he was head of a Max Planck Institute then. And he said, yes, please do. You were my idol in this arena. But she was unable to go back to it because of health reasons, and then she passed. But yeah, she definitely did a mic drop there.
Fascinating. Fascinating. Okay, so this has been a wide-ranging and very fun conversation. I want to bring it back to, like I said right at the beginning, I think that there's this really interesting moment right now where quantum theory is being put into practice in a technological way. If there were one concrete thing that you could tell,
asking a philosopher to do something.
I know, but that's the whole interesting thing is that they're making. I mean, in some ways, these are lab instruments that are testing our understanding of the universe, right? I mean, that's what Steve Gervin said in the morning. He gets into the lab and the first thing he does, he boots up the machines to make sure they can do something impossible, right? Like that's how he tests to see if it's working correctly. Is to violate Bell's theorem. So if there, I mean, you've talked about using more precision in language and words, and concepts. Is there one area in particular you'd say is the area to focus on if you're trying to build a quantum computer, that philosophy can inform?
Whew. Oh, geez. Saving the fastball for the
Sure.
end, huh?
Yeah.
I don't know how to speak specifically into that context, nor do I think it's necessarily appropriate as someone who's not got my hands on quantum computing technology. But I can say, I think learning and asking questions about the history and philosophy of the physics and not reading Barnes and Noble's books, although some of them are fine, right? Some of them are good, better than others anyway. But allowing yourself to be curious about these questions because the people who came up with these theories came up with them in the last century in virtue of their conceptual curiosity, their conceptual freedom. Einstein consistently says throughout his life that it is the freedom of the mind to sort of work between reason and data that allows the good scientists to make progress. So I guess, again, self-serving, but I think it's true. Ask those questions. Sit in on a philosophy of science class. Allow yourself to have that moment of creativity. But on a more pragmatic side, even though I'm not an ethicist at all, and maybe this is more important for AI and not specifically, but one thing is I hear a lot from engineers specifically in a variety of capacities that AI and quantum computing and whatever are just tools. And this is, I think, insidious because tools are right? Technology. It might be ethically neutral if it's understood in a vacuum, in isolation. If we're looking at a hammer all by itself, sure, maybe it's morally neutral. But the thing is, we don't create technology to be in isolation. We create it to be used. And so it is immediately put into ethical context. And so I don't care if you're an engineer who's coding and never whatever, like there are ethical implications to what you are doing. And this is rather serious. And so because there's so much funding going into quantum information science, and it is really exciting, we can also be human about it. And that means not just pausing to think about the historical philosophical context and why we love what we're doing, but to realize that even if we think we're using something in a morally neutral way, that's just not true, right? Our ability to use these machines and to use funding to build machines in this way is costing somebody somewhere. And we have agency in that. It's not like, we have agency to make good choices about it. So that's my sermon.
That's great. I mean, that's great because it connects directly to your description of how you, as you put it, your generation does history. That it's not, it's
Yeah,
rejecting the idea that these a singular effort, locked in a room comes up with
yeah,
a great idea. It's always, we are inherently social. We're inherently collaborative. We're all
yeah,
connected.
yeah.
Much like quantum um,
Yep.
subatomic
And
particles.
a lot of work goes into a small piece of achievement, and that work isn't always visible. It isn't always seen. Somebody was feeding Newton and clothing him while he came up with all this crap. Like somebody was paying his taxes for him. Like that's not trivial.
Well, also there's the idea of, I mean, interdisciplinary. It always bothers me that it's called out as like something special. It's like, no, literally, that's how everything is interdisciplinary. There's no such thing as a single discipline in isolation.
True.
Everything is both technical and philosophical and
Yeah.
science and humanities and
Yeah.
social and all of the
Now
rest of it.
granted, like the different disciplines have different training and expertise and methods and aims and goals. So yeah, of course, like nobody can be truly interdisciplinary and you pay a cost when you try to do that, right? There's a sacrifice in some depth, maybe. But that makes it all the more important that we have people in our chamber, so it's not an echo chamber, who have these different goals and aims and perspectives on the science, right? Because we need that. And that's what brings freshness to science. We know this from the history. This is what moves it forward is broader conversation. Yeah.
Yeah. Excellent. Well, a fantastic conversation, as I expected once again.
I talked too much. I get really excited.
No, not at all. The excitement is what is one of the key characteristics of a conversation with Elise Crull. So thank you so much.
Well, thank you for your lovely questions. And it was a good time, Sebastian. Let's do it again sometime.
Absolutely. Thanks again to Elise Crull for a genuinely fun conversation. The line I keep coming back to is the one about tools, that it's just a tool, it's ethically neutral move only works if you imagine the hammer or whatever the tool is in a vacuum. And we never actually build anything in a vacuum. That applies certainly to AI, and I think it applies to quantum too. And it's a useful sentence to keep in your pocket the next time you hear it in a meeting. This episode is brought to you by Outshift, Cisco's incubation engine. The need for computational power is rapidly increasing in every sector, from drug discovery to material innovation to complex financial modeling. Classical systems are reaching their absolute limits. It's time for a paradigm shift. The answer is a scalable quantum network built on open standards and a vendor-agnostic architecture. By uniting distributed quantum devices, you unlock limitless computational power. Learn more about the Cisco Universal Quantum Switch at outshift.com. Show notes for this episode are at newquantumera.com, including links to the Einstein paradox, Elise's recent papers, the Helgoland coverage we reference, and a handful of related NQE episodes if you want to keep pulling on those threads, particularly the Daniel Ladar episode on quantum noise, which I think is a useful technical companion to Elise's point about distinguishing decoherence from merely noise. While you're at the site, sign up for the newsletter. It's where I share what I'm reading, what's coming up on the show, and the occasional half-formed thought that isn't ready for an episode yet. If this conversation changed how you hear a word like entanglement or causality the next time it comes up, please subscribe wherever you get your podcasts and send it to someone who needs to hear it. Thanks for listening. I'm Sebastian Hassinger, and this has been The New Quantum Era, theme music by OCH. See you next time.